So, how much emissions does the grid generate? The figure here on the slide shows the historical and projected total amount of CO2 emissions globally and the contributions of various sources to these emissions. As you can see, electric power generation and transportation currently contribute to over 60% of the total emissions. To help reduce these major emission components, two transformations are underway. The first is the electrification of transportation through the deployment of electric vehicles or battery electric vehicles. Now, just electrifying transportation without reducing the emissions due to the electricity used to charge these electric vehicles isn't enough. The second major transformation is the decarbonization of the electric grid, which involves increasing the penetration of solar, wind, and energy storage on the generation side and distributed energy resources on the consumer side. DERs, or distributed energy resources, refer to different types of small scale electric devices and appliances that can generate electricity, such as rooftop solar PV, store electricity, such as the Tesla Powerwall, and whose energy consumption can be flexibly reduced or shifted, such as EV chargers, HVACs, and water heaters. Just to understand these trends of the transformation, and before I talk about the 21st century grid and its challenges, I'd like to show you the growth forecasts of these new resources. The figure here shows the needed reductions in carbon emissions to achieve the goal of reducing the rising temperatures to below 2 degrees centigrade by 2050. Two important observations that are relevant. 54% of the reduction in carbon emissions is achieved by increase in renewable energy and electrification of transportation. And 40% is by energy efficiency measures. To quantify the increase in renewable energy penetration needed to achieve the projected carbon emission reduction, this figure shows the projected annual amounts of electric energy from various resources. Two things to observe here are: one is that the electricity energy consumption is expected to grow by a factor of 2.5 by 2050. This is driven by increasing the demand for electricity in the developing world and the electrification of transportation and other sectors. And two is that the amount of electricity consumed from solar and wind resources will need to grow very significantly to almost 75% of all generation. As shown here, 45,000 terawatt hours of energy. We now switch into the electric vehicle growth forecast. The figure here shows the projected market share increase in various types of electric vehicles worldwide. In particular, passenger cars are projected to grow to over 30% by 2040, and more impressively, electric buses are projected to increase to more than 65%. This growth is driven by the incredible advances in lithium ion battery technology, which is what we use in every portable and mobile electronic device and corresponds to a huge projected amount of additional energy consumption of 1,290 terawatt hours of energy. The expected increase in EV penetration will require a very significant increase in the number of EV chargers, which is a large component of DERs. These two graphs shows that the EV charging infrastructure is expected to grow very significantly by 2040. You can see that worldwide we expect to see about 300 million connection points at home and at work, and 12.5 million public connectors around the world. They also show these figures show the projected split between home and work level 2 chargers and the public fast chargers. Notice that we are expecting a lot more connection points at home and work as compared to public charge. Just as a point of comparison, there are 500,000 gas stations in the US, and on average, they have 6 pumps, leading to about 3 million connection points. We have far more charging infrastructure than traditional gas infrastructure. Finally, another important trend that's driven by the increase in renewable penetration and enabled by the lithium-ion battery revolution is the increased penetration of energy storage in the grid, which is crucial to addressing renewable energy variability, as we will see in a moment. Most of the growth will be on lithium-ion battery storage. There are multiple types of storage, but most of the growth is on lithium-ion battery storage. You can see here in the graph that we are expected to reach about 4,000 gigawatt hours of battery storage, and the majority of it will be on utility scale batteries, and a small but non-negligible amount, about a quarter, on commercial and residential batteries, which are installed at the customer site. Just to recap, to achieve less than 2 degrees Celsius temperature rise, renewables and EVs will need to grow significantly. Renewables are expected to grow from 2,300 terawatt hours that they were in 2019 to 45,000 terawatt hours by 2050. EV penetration is expected to grow to over 30% of all vehicles by 2040. DERs, distributed energy resources, will represent a very large and rapidly growing energy resource. Distributed solar PV, the rooftop PV, and storage, our power walls, expected to reach about 3,000 terawatt hours by 2050. EV chargers are expected to consume 1,290 terawatt hours by 2040. And then we expect hundreds of terawatt hours of flexible loads. Just as a point of comparison, all the data centers we have in the world today consume about 200 terawatt hours, and the Stanford campus consumes about 200 gigawatt hours in a year, which, it's about 0.2 terawatt hours. These transformations will lead to significant challenges for this 21st century grid. Let's see what are these challenges. Here you can see our traditional grid and the traditional operating paradigm. We have generators and utilities meeting at wholesale markets, the system operator dispatching the generators so that they meet the predicted demand while satisfying transmission constraints. Once that is done, all the power flows from generation to customers through the transmission network and through the distribution network. That's our traditional system. But the grid is changing significantly, as we saw. First, we are adding a significant amount of renewables as well as electric storage at the transmission level. Then, at the consumer side, we are seeing the adoption of electric vehicles, shown here in the picture, of smart appliances. For example, you can see here a smart thermostat, and the capacity to produce power, not just consume, through, for example, solar PV. And more importantly, all of these technologies on the consumer side, which are all behind the meter, so they are known as behind the meter technologies, they're all connected to the cloud, which allows us to monitor them as well as control them. And if you can control and coordinate these technologies across multiple consumers, then this can become a resource that can participate in the wholesale market, creating a whole new type of flexible demand that is only available in very limited ways today. So just to recap, major changes that are happening for the 21st century grid: a lot of adoption of renewables, adoption of storage systems of different types of storage, and the increased deployment of distributed energy resources or behind the meter resources that are connected to the cloud and can be coordinated to offer demand flexibility. When these changes happens, what are the issues that arise due to them? The first and most important issue is that we have to ensure that the grid becomes stable against the intermittency of renewable generation. You can see here, the traces of two sources of renewable power. On the top, we have wind. On the bottom, we have solar. Renewable power is both variable and intermittent. You can see the variability here on the wind power, which is throughout different hours of the day because of the environmental conditions. Different amounts of power is being provided by the wind turbine. The power is also intermittent, as shown here in the solar, where you can see that throughout the day the solar increases and decreases due to the position of the sun. But more interestingly, you can see sudden power drops, which in this case correspond to clouds passing by your solar power plant. Being stable against this variability and intermittency is going to be very important. And that means dealing with the power ramps that are naturally observed, as well as the sudden losses of power events. One new issue that appears in the 21st century grid is the issue of backflow. Backflow means if consumers have rooftop solar and collectively they produce more power than they consume, suddenly power is flowing from the consumers back into the grid and potentially even back into the transmission network. This has never happened before, and it means significantly rethinking how we engineer the system to ensure that we are stable and reliable. The next big issue that once stability is ensured is cost. How do we operate the system with deep penetration of renewables and DERs so that costs are either maintained or even further reduced? Resiliency and overall network reliability have to be ensured. And in the process of operating and ensuring reliability, resiliency, low cost, and stability, we should keep in mind the energy efficiency and emission goals. Overall, in this 21st century grid, we need to ensure the security of the grid as well. That's another major issue. In order for all of these to happen and for us to have viable business models for the future grid, we need to have pricing mechanisms and market structures that can integrate all of these new technologies. And the regulatory framework has to be enabled to support these mechanisms and market structures and ultimately support the business models of the generators, smart loads, etc., to mitigate the variability of renewables. Finally, all of this will not be possible unless we have people's acceptance. So educating consumers and helping them understand this transition will be a very important issue to address. I want to now spend a little bit of time going into more detail into some of the key issues caused by the deep penetration of renewables. The first one that I want to talk about is that typically when you add a lot of wind and solar generation into your system, you would like to know whether they're correlated with the demand. And in fact, wind or solar are typically poorly correlated with demand, and as I mentioned before, they are intermittent. As illustrated in this graph of 30 days of electricity demand in red, solar in yellow, and wind generation in blue, renewable generation and demand are poorly correlated to electricity demand and are intermittent. These present significant challenges to the reliability and efficiency with which the grid operates. One of the challenges of the poor demand correlation with the renewable generation is the so-called duck curve, which refers to the shape of the net load in the grid or part of it in a typical day due to solar generation. As you can see here on the figure, the net load decreases dramatically during the day when the solar is high and then must ramp up very rapidly in the evening as loads increase and solar decreases. So the generator needs to ramp down during the morning and then ramp up dramatically during the evening to address these duck curves. These lower valleys and higher peaks require high generation ramping and cause voltage fluctuations, which can damage the transmission and distribution grid infrastructure and loads. Another challenge of the poor correlation of high renewable generation and the demand is curtailment. For high total solar and wind penetration of 55% here on the graph, as you can see, if I go to 55%, a significant amount of power is being curtailed. You can see here about 60 terawatt hours. And in this study, this was done for ERCOT, the Texas system operation. Even if you optimize the mix of wind and solar, which has been proposed as a solution to this problem, you still curtail a lot of production because it does not match the load. This results on a waste of resources. So we definitely need to address this issue. Finally, the challenges caused by the high EV penetration are discussed on this slide. To quantify the increase in load due to high EV penetration, we use a simulation model developed under the Bits and Watts EV50 project at Stanford. As you can see, the grid peak power is expected to increase by 25% as we have the adoption of electric vehicles, which results in significant transformer overloading. Moreover, fast charging can result on large local voltage spikes, which can damage the equipment that is deployed in the distribution grid to ensure reliability. If we assume that each public charger serves about 5 drivers and each workplace charger serves about 2 drivers, then 80% of the drivers have access to home charging, 5% also have access to workplace charging, and 15% on public charging. And those are the numbers used to generate these impact estimates right here. How do we address these challenges? Recall that to match supply to demand in the grid, we schedule power at different time scales. This is depicted in this cartoon, which shows how demand is met by a combination of base generation and reserves, most of which use fossil fuels. You can see here for the 21st century grid. With high renewable penetrations, here you can see in green the high renewable penetrations, we are able to replace some of the base generation, but it certainly increases the reserves. This is somewhat mitigated if we are better able to forecast renewables and use energy storage. But this increase in reserves overall results on an increase in the cost of integration. Let's see what do we mean by cost of integration. Currently, the system is operated by a 3 sigma rule. We predict the loads, and the load error forecast about 2%. And you can see here, we are forecasting this much load, and 2% error is indicated by that stripe in black. And in the 3 sigma rule, we schedule power beyond the forecasted load by adding about 3 sigma on the error. So in this case, we would schedule reserves of 6%. That's 3 times the sigma of the error here. Now, what happens when we have an increase in renewables? So typically, this results on, in the existing system, on about $300 million in reserves for CAISO, for the California system operation. But what happens when we have renewables? We now forecast the net demand, which is the load minus the renewables. We have to predict both the loads and renewables. The error is larger because we have the error of predicting the loads and we have the error of predicting renewables. And as we saw before, renewables are quite intermittent and can cause a lot of variation, resulting in harder to predict errors. Larger errors means we have much larger reserves that are required. And that would result in an additional spending of $700 million annually at the California system operation. In these examples here, we just added 25% wind to our existing system. And notice the error went from 2% to 7% because we predict the load and wind. But by the 3 sigma rule, we go from 6% reserves to 21% reserves. So the cost of integration is the cost of scheduling reserves as shown here in red. This is called the cost of integration. Reducing the cost of integration is the essential challenge for the addition of renewables. So just to recap, what are some of the key challenges when we talk about deep decarbonization of the grid? The first one is how to reduce the cost of integration. The second one is when we have these deep penetration of renewables, what happens to electricity prices? And finally, as we saw before as well, how do we replace baseload with clean power? As you saw, each time we replace baseload with renewables, we have to add a ton of reserves. So this is also in a way related to the cost of integration. Let's look at each one of these challenges and discuss them a little further. So there's 2 ways of ensuring a major reduction in the cost of integration. The first one is to improve the forecast of renewables. If we can very accurately predict renewables, then certainly that total error reduces, which means that overall we have to schedule less reserve power. Another alternative, because there's going to be a limit on how much we can improve these forecasts, is to actually add storage. So you can see here in the picture that we have the duck curve and this is data from the California system operator. If somehow we could store power during the red hours, so we increase consumption, and then use the store power on the hours shown in gray here, then we would flatten the load, remove these ramping requirements, and most likely reduce the curtailment of electricity. So that's one option, to use electric storage to reduce the duck curve. Another option is to see whether we can actually flexibilize demand, which means whether the demand itself could be shifted to the hours of high renewable. And we will see both of these options as we discuss storage and flexible demands. The next question is, what happens to electricity market prices with deep renewables? If at any particular hour or day, too little renewables are produced, so the system, the power system, the generators, the renewable generators are not producing their typical amount of power, maybe they're producing below, then we expect that the demand exceeds renewables. And that means we have to run traditional generators. And these traditional generators will set the electricity price because the electricity price is the marginal cost of the most expensive generator dispatched. So in this case, we are in a very similar world as what we have today. Renewables reduce the overall demand, but electricity prices are still determined by the marginal cost of expensive generators. It's worth noting, though, because when we have deep renewables, you saw we have a lot of ramping. The generator that ends up being dispatched is typically the most expensive overall because they have the ability to ramp up and down. Now, if the exact amount of renewables are produced as of what we have as demand, that means the demand matches renewables. We have 100% renewable hour in the grid. What is the electricity price? Well, the electricity price is the marginal cost of generation, and the marginal cost of generation of renewables is zero because once you build a renewable power plant, it's going to produce what nature induces it to produce. It does not depend on any marginal cost. So for the hours where the demand exactly matches the renewables, the electricity price is zero, which means for those hours, renewables make no profit. If too much renewables are produced, meaning we have a particular hour where there is more renewable production than demand, then we have again a grid imbalance and we have to curtail the renewables. We have to reduce the renewables or increase the demand because you have to ensure that demand matches supply at all times. Now, paying to curtail renewables or paying to increase the demand means the electricity price is negative because you're paying for someone to consume electricity. So we end up having negative marginal prices. So when we move from the existing market model to one where there is a deep penetration of renewables, we can face either zero marginal costs or even negative electricity prices. And this will lead to different patterns of investment and operations, but it's very important to note that typically it's very advantageous for renewable power producers to bid less power so that they ensure we end up in this first situation. So this is being observed in the existing markets today, that if we end up with very high penetration of renewables, renewable generators curtail their bids to ensure positive prices and a profit. So we have to rethink the electricity market if we want to support very deep penetration of renewables. The last question to address here, as a major issue when we are talking about the decarbonized grid is how do we replace the actual significant amount of baseload? So the baseload generation, as I mentioned earlier, is generation that changes very slowly, so it's extremely cheap. And it comprises a significant portion of the amount of power that we schedule every day and every week. For example, California has 48 gigawatts of firm capacity, and 42 of those 48 gigawatts are coming today from natural gas generators and 2 gigawatts from nuclear. Nuclear is decarbonized. Now, how do we decarbonize this firm power or baseload power? In this study, a very interesting study done by some colleagues at Stanford and Princeton, they show there are different options one can consider. The first option is a all renewables option. Try to replace these 48 gigawatts of firm capacity with renewables. That means you have to significantly overbuild renewable generation, and that results on electricity costs of about 15 cents per kilowatt hour. That's way above our electricity rates, our tariffs today, which is about, on average in California, 9 cents per kilowatt hour. And then you have many different options, as shown here. You can have the baseload coming entirely from nuclear, which would keep our rates close to what we have today, but in a completely decarbonized system. You could have, for example, electrical clean fuel, so hydrogen, for example, and that would result in perhaps close to or a little bit exceeding what we have today. Or you can have system that has carbon capture with nuclear, as shown here in the fourth bar. And again, that's another option that either, depending on the model you use to study, the cost is similar to what we have today or a little bit less. And finally, you can have a system that's purely natural gas generators with carbon capture, which again would result in a very similar rate as what we have now. So overall, we have to consider a mix, which is renewables with either a nuclear, different hydrogen, and potentially carbon capture, if we want to be able to have clean firm capacity delivered at the current electricity rates that we see in the grid.